In this video, I'm going to give you a basic introduction to evaluating numeric expressions and numeric types. The Python interpreter is an interactive environment that uses a read, evaluate, print loop, or REPL. This is similar to how one interacts with a calculator, so we're actually going to start with how you use the interpreter just as you would a calculator. For example, if I were to write 2 plus 2 in this code block, and then run the code block, the interpreter will read the entered text, 2 plus 2, it will evaluate that expression, and then it will print the result before looping back for more input. If we were to do this in an interactive session with the Python interpreter, then we would see the primary prompt returned to us immediately after the output, indicating that the interpreter has looped back and is waiting for more input. In Jupyter here, we don't necessarily see this loop back behavior because we interact with the interpreter via these code blocks. But in the background, the read, evaluate, print loop is still in effect. Python supports the typical set of operations like addition, subtraction, multiplication, and so forth. So if we enter 8 times 5 minus 10 divided by 2, Python will of course evaluate this according to the operator precedence. In our example, the multiplication and division operations are evaluated before the subtraction, so running this block gives us the result 35. Now if we wanted to change the order in which these operations occurred, we can of course use parentheses. So if I wrap the multiplication and subtraction with parentheses, then 8 times 5 minus 10 is evaluated prior to the division, now giving us 15 as a result. If you're interested in seeing a full list of the operators and their precedence, then I suggest you check out the link here at the top. Now, one more thing I'd like to point out here is that in the first example, the inputs to the expression were integers, 2 and 2, and their output was also an integer, 4. But in the second example, we still had integer inputs, yet the result returned was a floating point value. So why is there a difference here? Python 3 will actually convert integers to floating point if you have mixed integers and floats in your expression, or if you're performing certain operations, like division. So our second example contained a division, which prompted Python to upgrade our integers to floating points. And this is actually a difference in the behavior between Python 3 and Python 2. In Python 2, if all of your inputs to a division were integers, then the result would actually be an integer. That is, Python 2 would actually be performing floor division with its integers, meaning the result of the output would be rounded down towards negative infinity. So we look at another example. 17 divided by 3 gives us 5.6 repeating. And we see that Python 3 here has upgraded our integers to floating point. In Python 3, however, if you do want to perform floor division, you can still do this, but you need to use a different operator. In place of the single slash for division, the floor division operator is 2 slashes, or the double slash. So if I write 17//3, you'll see that we now get the integer 5 as an output. Okay, we can also get the remainder of a division using the modulus operator. And to do so, we write 17, use the percent sign for the modulus operator, and then 3. And you'll see that we get a remainder of 2. For the last examples in this section, I want to talk about exponentiation. And the reason for this is Python actually does this a little differently than what you've probably seen in other languages. Python uses the double asterisk to specify exponents. So if we wish to write 4 squared, we write 4 asterisk asterisk 2. And this operator actually supports floating point values as well. So for example, we could write 3 raised to the 2.1 power. In addition to integers and floating point values, Python does have built-in support for complex values, and it denotes a complex value by using the suffix j for the imaginary unit. So we can write 3 plus 5j, and in the output it uses parentheses to help us understand that this is in fact a complex value. And of course, these can be used in arithmetic expressions. So I can write 4.25 times the complex value 3 plus 5j. And I'll use parentheses here so the multiplication is applied to both the real and imaginary components of this value.